So welcome everyone today to our webcast. We have ASCENT author Scott Hendren with us today to talk about motion analysis using behavioral modeling in Creo Parametric 3.0. Scott is a Creo expert and the author of all the ASCENT Creo courseware, so we're pleased to have him with us in today's session. So Scott, if you're ready, I'll pass the floor over to you.
Thanks, Corinne. Can you hear me?
I can hear you very well.
Okay, great. So thanks for joining in, everyone, today. We've recently released a new title, Behavioral Modeling with Creo Parametric. And what I'm going to do today is go through the motion analysis lesson from that course with you. So what I want to do is kind of go through the content that's there, as well as one of the exercises from the course, and kind of give you a flavor for what is in there. So what we can do with behavioral modeling, as well as the MDX, the mechanism design extension, is to run analyses on our assemblies as they move through their range of motion. And we can use behavioral modeling to modify dimensions and parameters to achieve various design goals that we might have. So for example, you can use MDX along with BMX to study the effects of the motion of your assembly on the center of gravity and what happens to that center of gravity as the model goes through its range of motion. Another example would be to study the clearance of components relative to one another, again, as the model goes through its range of motion. So what we will be doing is producing maximum and minimum values of our parameters over time as the model goes through its range of motion. And we can also do things like display motion envelopes so we can see what that motion will look like. So to sort of combine MDX and BMX, so MDX, Mechanism Design Extension, BMX, Behavioral Modeling Extension, we first do our motion analysis. So we create an analysis feature, set the type to motion analysis, which then opens up our motion analysis dialog box. And in here, we select the parameters that we want to evaluate. We can apply some additional options, so we can do collision detection or, as I mentioned previously, create a motion envelope. And the system will evaluate the parameter that we've selected as the model runs through its range of motion. Once we've completed that range of motion, the system will provide for us several parameters, and we can decide result parameters, and we can decide to choose to produce those parameters or not. So, for example, something that we'll be looking at will be the minimum distance between a couple of components. So we can choose to create that parameter and then evaluate what's happening with that parameter through the range of motion. The two sort of pieces of behavioral modeling that we'll look at specifically will be a sensitivity analysis. And what the sensitivity analysis will do is it shows you how a parameter reacts when variables are changed through a specific range. You then take that information and it gives you sort of your best starting point for doing a feasibility or an optimization study. And what we'll use in our example is a feasibility study where we adjust a variable, and that variable is adjusted to meet our specific design constraints that we come up with. Something that's kind of critical about that is the system will stop evaluating once it's reached its first successful solution. If you have multiple variables, there could be a whole lot of different ways in which a solution could be derived or could be arrived at. But a feasibility study is just saying, is this feasible? Does this work given the constraints that we've put on the model or on the analysis? So as I said, we're going to go through this motion analysis example that we have from the guide. And it's a fairly straightforward analysis, and it's something that all of us are familiar with, just a doorknob mechanism. And we want to look at a couple of things within this mechanism to make sure that it's suiting our design goals, doing what we want it to do. So I'm going to jump over to Creo here. So I have my assembly, and the two things that we want to look at that are critical to us in this particular example are this component slides in and out, which obviously lets the door open or latches it closed. There will be a spring added to this assembly that pushes this to its closed state when you release the handle. So that spring that we're going to add into this assembly has a compressed length of 0.2 inches. So what we need to be sure of is through the range of motion of this assembly that, oops, sorry for the flickering here, that this surface at the end of this cylinder is at least 0.2 inches away from this stop part. So we have to be sure that that happens during the range of motion of the assembly. The other thing that we have to do is make sure that when this is in its open state, the edge of this slider is flush with this plate. Because if it's not flush with this plate in its open state, the door won't open, or at least it'll catch when you try to open and close the door. So those are the two things that we want to evaluate within this assembly. So the first thing we'll do is go into our mechanism application, and we'll apply a playback. So we have the motion already stored, so we'll open that up. And we'll run the animation so we can see what happens with the geometry. And we'll speed this up just a little bit. And hopefully that comes through okay over the WebEx. But this is the motion that the door handle goes through. And as I said, one of the key pieces to this is when this geometry, or when the handle is in its open position, the edge of this has to be flush with the plate just to make sure that this doesn't catch on anything. And as we can see here, currently that's not the case, right? It doesn't completely go inside of the plate, so we have a bit of an issue. So we'll go into our analyses and take a look at what we can do to kind of remedy these two or verify these two states. So we go into the Analysis tab, and the first thing that we want to do is to create a Measure Analysis feature. So we'll explode the assembly. We're going to create a measure analysis that measures the distance between the stop plate and the back of the cylinder. So we can measure the distance between this surface and this surface, and we see that it comes out roughly to 0.5 inches to start with. So we want to be sure that we create that distance as a parameter. So we select Feature in the Measure dialog box, and we can set the name of this to distance _1 because later on we're going to create another distance parameter. A couple things that are really important within this dialog box that can cause you trouble down the road. When you enter a name for this parameter, and you don't have to change the name. You can certainly keep the default name if you wish. But if you want to change the name of that parameter, there's two things. One, make sure you hit enter after you've edited the name. The second thing is we're going to save this. Be sure that you change the name before you save the measurement feature. If you don't, if you save it first and then you change the name, that change that you make doesn't get recorded. So we change the name of the parameter and then we save this analysis feature. Okay, so we'll call that measure 1. So that measures the distance between the two components. It can't do it in the exploded state, so we just have to confirm and it'll put it back to unexploded. And then we're all set. So now we have an analysis feature that's measuring that distance. So now we want to use that in conjunction with our motion analysis. So we'll create an analysis feature. We'll name this motion 1. And of course, select a motion analysis. We click next, and that puts us into the motion analysis dialog box. So here, what we want to do is look at what happens to that distance parameter as this moves through its range of motion. So we select the distance parameter, and then we simply select run. So as you would expect, it's just a sort of a cyclical motion. In the 3 seconds that have been allotted for this, it moves in, or starts in the out position, I guess, moves into its tightest position, and then it moves back out again. So as we discussed previously, what is important for us is that the distance between the back of the cylinder and that stop component has to be at least 0.2, because when we put that spring in there that pushes the cylinder back out every time you release the handle, it does have a compressed length. It does have a fixed length when it's compressed that we have to allow for. And we can see when we look at this motion analysis that most definitely that spacing is not allowed for, because we hit 0.2 at this time and we move well past that as we continue through the motion. So what we're going to want to do is actually edit the geometry to account for this and make sure that that actually fits the way we need it to fit. So we can close this, close the motion analysis, and here we want to create a result parameter from that motion analysis. So what we'll do is create a parameter for the minimum distance. And we can leave just the default name as min distance 1. So we complete that. And now what we want to do is, and we certainly could do this by just a trial and error way, but why not let the software do it for us? We want to go through, run the geometry through multiple iterations, multiple changes to the geometry to see if we can come up with a solution that fits our requirement, keeping that minimum distance of 0.2. So we're going to run a sensitivity study and see what happens to the dimensions. So we'll do a sensitivity study or a sensitivity analysis. So I've already, in this particular case, I've already selected the dimension. Just so I can show you which dimension it is. So we have this 0.875 dimension. That dimension will be increased or decreased, which will move the flat part of this cylinder to adjust so that we maintain that minimum of 0.2 between the flat here and this stop part back here. Apologies. So we'll create our sensitivity study. We've pre-selected that dimension. And to add your parameters, we want the minimum distance for that analysis. So that's been selected. We simply click Compute. So that will run through on a range of values from 0.875 to 1.1. Give it one moment here. Normally this is a lot faster. I don't know if it's because of the presentation piece of this kind of slowing things down, but normally this would run a little bit faster than what we're seeing here. Okay, so that has completed. And as we can see, we want that minimum distance to be 0.2. So within that range of values that we've selected, the 0.875 and the 1.1, there is a dimension value that meets our requirement for that minimum distance. So we know by running this sensitivity study that, yes, the range that we have will get us a viable result. So we can close that, and we can close the sensitivity study. So now what we want to do is define actually what value for that geometry that we have exactly gives us what we need. So we can do a feasibility study, and we add the parameter that we want to look at, and that parameter that we want to look at is the minimum distance from analysis 1. And we want that value to be 0.2. We then also have to add the dimension. I can explode this to easily select it. And we'll set the range of values again to 0.875 and 1.1. Middle click to finish selecting your dimensions, and then we want to look at some of the graphing options. So within options, select our options. We select our preferences. We want to graph the variables, and we want to set a convergence of 10%. So that means that any consecutive values that are within 10% of one another, that will consider it converged, or consider a solution reached. We compute. Again, this will just take a moment. It seems a little bit slower, of course, as we're doing this presentation than it did earlier today. But again, this is a fairly simple example. So, within 3 iterations, it converged on a solution. So at this value, which if we look in the bottom left, editing that dimension to 1.0767 will give us that clearance that we required. So we can close this. and close the feasibility study. And what happens when you close that is it gives you some options here. As it's running the feasibility study, it's actually in memory regenerating the various instances of the model. So it's changing dimensions, regenerating, changing dimensions, regenerating, et cetera. So once it's converged on a solution and you close this dialog box, the system wants to know, do you want to go back to the original dimensions? Do you want to use the dimensions that we've established as being a solution for your study? Or do you want to just cancel this altogether? So what we'll do is we'll confirm this and have it regenerate the geometry at the value that works for us. So we can actually take a look at this. And we see that it's converged or edited that value to the 1.077 that was brought up in the analysis. So again, instead of us going in here and manually editing that dimension until we arrived at a solution that worked for us, we let the system do all of the hard work and do that analysis for us. Activate the assembly again. So the second piece of this, so that'll take care of giving us the correct spacing for that spring that we need. The second piece of this is to make sure that this slider actually goes into this plate and sort of tucks itself inside so that it doesn't get caught when you try to open the door. So we'll create another measure analysis. And again, we'll measure the distance from this point that's been added to this surface. Call this parameter distance 2. And we'll call this measure 2. So we know what the distance is in its current state, so we can close that. Now we'll create a motion analysis. We'll call this one motion 2. Obviously, make it a motion analysis. Oops. There, I didn't take my own advice, and I didn't hit enter after I entered the name, and you can see that it reset it on me. Okay. So in this case, the parameter that we want to look at is the distance 2, measure 2 parameter. So we can run this. And as with the other motion, where it's cyclical, it looks exactly the same. Obviously, this distance is different than it was with the slider. But we see what the motion analysis is. We can close that. And again, we want to create this minimum distance parameter. Now, what we will do this time when we do our feasibility study, and we certainly could do another sensitivity analysis, but we know it's just going to be a linear relationship. And to save time, we'll just jump right into the feasibility study. So we'll do another feasibility study. Something that's important about this dialog box is where we already have a feasibility study. When you select this option, the previous feasibility study fills out this dialog box. So you'll want to just click New and create a new design study. Otherwise, it puts you back into the previous. So here, we want to add the distance to motion 2 parameter. And we want to set that value to 0. So that means that when this is in its open state, there won't be any distance between the edge of this latch and this plate, so it doesn't catch on the door. So fine, we'll click OK. The dimensions that we want to add here is this overall length. And we'll use a range for this of 2.25 to 2.3. For our preferences, oops, I'm sorry. Set this up as an optimization study. It should be a feasibility study. For our options, we want to graph the variables, and we'll set the convergence to 0.1 and compute. So again, it'll take a little bit of time to go through and run the analysis. Again, where it's fairly simple, simple assembly, it'll converge quickly. And we see that it's converged at a value of 2.28. So if we close that and we confirm the change, so again, that will leave this geometry regenerated with that new dimension value of 2.28. We should see that when we run the analysis, run the motion, we can go back to our mechanism, and we can play back the motion. So when we look at this at its peak, it goes to 0. All right, so we now have the clearance we need, and we know it's not going to catch on the door. So by using behavioral modeling and using our mechanism design extension, we can control our assemblies, we can look at various scenarios, and as I mentioned, it simply allows you to avoid doing manual investigation on and manual edits and regenerates. It does all of that for you. So that is the exercise from our behavioral modeling motion analysis chapter. Before we kind of give it back to Karine, just to go through, these are the titles that we have for Creo Parametric 3. We will have those same titles, of course, for Creo Parametric 4, in addition to an update course that we're currently working on for Creo 4. And there are a couple of other titles that we may also be adding to the library. No, not necessarily a confirmation of that just yet, but we're looking at investigating ISDX as an offering for the upcoming year.
Excellent. Thank you, Scott. If you want to go to our next slide, I just really quickly wanted to show everyone all those titles you just showed us and the book you just taught from, which was the Behavioral Modeling for Creo Parametric 3.0. We have them available as a printed spiral-bound book, or actually you can purchase it from Amazon, and it's called Perfect Binding on there. And they call it a student guide. It is ASCENT. It's referred to as a student guide. That's the printed version of the training guide. We also have ebooks, which contain the same content as the printed guide, but in a digital version. We've got an image there of someone using it on their iPad. And we also have instructor tools that Scott has put together as well. So if you were tasked with teaching this as a class or as a course, then the instructor tools are helpful. They're an additional piece that you can purchase to complement the book. They include timing suggestions for delivering the class and all the answers that are to the questions that are posed within the book. And lastly, on our last slide here, again, just want to show everyone how they can reach out and contact ASCENT and where to purchase from us. So the first link that will come up here is our e-store, and you can also purchase from Amazon as well. If you go to our website, which is the bottom link there, ASCENTED or ASCENTED.com, you can access all the information about our books there, table of contents, sample chapters. You can read about the book, and you can make purchases directly from there. It'll take you over to either our e-store or to Amazon. And if you have any topics you'd like to hear us discuss here in a webcast or any books that you'd like to see ASCENT write, please drop us a line at courseware@ascented.com, or of course you can call us. We love to hear from our customers. We love to hear feedback, and many of our courseware is written based on customer feedback. So we are listening and we are here.